Okay, good morning everyone. This is the MTE 4598 TEM laboratory on video, and this is the Joel 2100F field emission gun TEM that is in MSEM, and I'll give you a bit of a description first. Up the top we have the electron gun, which is where the filament is, and so that's the cathode. And then you've got the anode, which does the accelerating, and then the electrons move down the column, which is the great big column thing that you can see here. The specimen sits in here. You've got a sequence of apertures, and I should actually start with, you've got the condenser lenses here, you've got the condenser aperture, you've got the high contrast objective aperture here. You've got the objective aperture here, this is where the specimen sits, and so the objective pole pieces are here, and the aperture sits in the back focal plane of that objective lens. You've got the selected area aperture, which is used to select the area on your specimen from which you take your diffraction pattern. Then you've got the viewing screen. You've got a series of detectors right behind this plastic sheet. I'll explain why this plastic sheet is here in a moment. You've got one high-angle annular dark field detector, you've got an annular dark field detector here, and then below that you've got a camera. Now it's a digital camera, but this can also take film, so good old gelatin film. And then below that you've got the digital camera, which just fits in under the viewing screen, and then underneath that, further still, you have all the electron optics. The electron energy loss spectrometer, the Gatan Infina, which allows you to do electron energy loss spectroscopy, or EELS. Over here we've got the EDX detector, which is kept cold by this dewar filled with liquid nitrogen. Now, I was going to explain why this piece of plastic is here, and that is to stop the drips coming, and also the liquid nitrogen spouting out of the cold finger. Before we start the microscope session, everything is under high vacuum, so there are some scroll pumps in the service rooms out the back there that service the ion getter pump, as well as a number of other pumps that service the microscope. I think there are about 3 or 4 pumps on this microscope to keep it at super low vacuum. But this is a cold finger, which is maintained at liquid nitrogen temperatures, and it contacts the column, and it means that anything left in the system, gas, water vapor, and there's always a little bit, because you can never make a perfect vacuum system, that will condense out on the cold finger. And at the end of the day, when we run through a heating cycle, that all gets evaporated off and trapped by the other pumps. So this sheet is actually here from the last user. This is the state in which you walk in the morning to use the microscope, and this sheet was left here from the last user because they had to do a cryo cycle. They had to heat up the cold finger and drive off all the liquid nitrogen, and that means the liquid nitrogen can fly everywhere, because it comes out of a little hose up here, and I'm a good scale bar to show you how tall this is. You can't see the top of the column because I couldn't move the camera tripod far enough back or zoom out far enough to see the very top of the column, but the bit that's cut off, there's probably another foot of gun above the frame of the video. So this sheet is here because I'm about to go and get some liquid nitrogen and start the crucial part of the process of starting up the instrument. Now, startup takes quite a while. We have to put a specimen in, we have to cool the cold finger down, we've got to start detectors, we've got to check that the water flows are correct, check the vacuum is correct. There's quite a lot to do. So I'm going to very quickly lead you through that process. In order to do that, it's a bit like flying a plane. We have a checklist, right? So every pilot, when they fly a plane, They go through a pre-flight checklist, and those checklists are an industry standard so that the pilot doesn't forget something and crash the plane. It doesn't matter how much experience the pilot's got. They need to run a pre-flight checklist so that they haven't forgotten anything. We're only human. So that's the same with a microscope, a TM especially. It's quite a complex piece of instrumentation, and if you forget something, if you forget to do something like switch down a gauge while you're transferring specimens and there's a bit of a leak, you can shut down the microscope or ruin a gauge or ruin a vacuum pump, and these things are usually quite expensive to fix. So a microscope like this might cost of the order of $3 or $4 million US, so about 5 million Australian dollars, and damaging any part of it can cost hundreds of thousands, especially the gun. We recently had a new gun put on this microscope. Guns are usually worth around about $300,000 to $350,000, and they're flown from the factory in Japan in shockproof crates with all under vacuum. So the gun is continuously under vacuum while it's fitted on, while it's in transit, and while it's being fitted onto the microscope. And so the tip in there, which is almost atomically sharp, is never exposed to atmosphere, which would destroy it essentially. So anyway, I'm going to run through the pre-startup checklist. I've got a logbook that I need to fill in because every little hiccup, all the conditions need to be logged, because that's a way of keeping track of whether the filament is losing its brightness and whether a new filament is necessary, etc., etc. So I'm just going to check the user log for the last user. Looks okay, no problems reported, and then I'm just going to run through the startup checklist. I'll keep the camera rolling, and I'll talk you through a little bit, but maybe I might not show all of this in the final edited version of the video. Okay, because it could be a very long video, because TM sessions this one will take all day. So I'm certainly not going to make a video that lasts 8 hours for you to watch. Okay, but I think startup is quite a useful thing to show you. So without further ado, I'll run through, put these things down, I'll run through the startup checklist. So the first thing to do is turn the pumping station off. Now the pumping station is where the specimen holders sit under vacuum. And I will move the tripod around and try and show you where the pumping station is. It is over there. So that's the specimen preparation, specimen loading bench. And in that far corner where all the papers are up on the wall is the pumping station where we keep the TM holders that we're going to use. And I'm going to use a double tilt holder. And I have to turn that off so that it vents to vacuum. So just close the valves, turn the pumping station off, and this is the holder we're going to use, this one here. I'm not going to move the tripod because that'll stop us viewing the microscope. So now I'm out of shot, I'll return us to the microscope, and I'm going to zoom out again. And that's about as far out. Now I'm going to check over there. Those are the supplies. That's the water. In the service rooms there, we've got the pumps. And at the back, we're going to walk around the back of the microscope. That is the high tension tank that takes the mains voltage up to 200 kilovolts. And that big cable there goes into the back of the electron gun. Okay, and so there's some valves up the top there, and the ion pump sits behind that shielding, that paneling right there that says GEM 2100F. and lots of cables running along the floor, going into the service rooms. We'll check the water. Okay, so this is chilled water that services the microscope lenses. All of those little bobs up to the line, so we can check that off. Next we need to check gas pressures. So there's the high pressure nitrogen, and that looks right, that's at 12 o'clock. There's the gun sulfur hexafluoride, which is an insulating gas. That's right on the red mark, so that's fine. There is the sulfur hexafluoride pressure in the high tension tank, and that looks fine. That's on the red mark. Now I'm sorry for the shakiness. Going to the vacuum monitors, the gauges. I'm just going to switch this gauge to 10 to the -5. It's funny doing this on camera. It's on camera. And that gauge there shows that we're at a nice pressure, 1.1 by 10 to the -5 pascals. So that's about 10 to the -11. Sorry, 10 to the -10 atmospheres. So now I can just close this door, or just I'm actually going to turn this down because I'm going to mount the specimen, and we don't want a gas influx to ruin the gauge. And I'll leave that door open. It makes a lot of noise. And okay, so now that we've got the specimen holder coming up to atmosphere, I'm going to put liquid nitrogen onto the microscope. First things first, I have to start filling in the logbook. Mustn't forget to do anything. Got to concentrate extra hard today because I'm on camera trying to explain it to you guys, and I've got to also concentrate on flying the plane, so to speak. So the date today, the 12th of the 4th. So the user is Phil, and it's MTE4598. Start time 8:15 in the morning. I actually got here at about 7:20, so there's a bit of prep involved. I'll just put down this project number that comes with the unit. We're going to be looking at an aluminium alloy. So this is the mystery aluminium alloy that is part of the consulting brief for Airbus Industries. AL alloy. That's the sample. Technique is going to be a mixture. TM. Selected area diffraction. Seabed. The holder is the double tilt holder. We're going to have to clean the specimen in a plasma cleaner. Cleanliness in TM is absolutely vital, so we use a plasma to clean the specimen. So argon oxygen mixture for 1 minute. The high pressure nitrogen was good nick. SF6 pressure fine. Water flow rates fine. The starting pressure on the column was 1.1 before putting liquid nitrogen in. I've forgotten what the other pressures were, so I'm going to have to go back to the cabinet. Sorry. 0.05 and 0. It just disappeared for a second there. That's 0.05 and 0. We're going to use it at 200 kilovolts. Okay, so now I have to turn on the status monitor. This is also the main microscope control software through this computer. I will explain everything more fully in a moment. And it's quite dim because when we're working in the dark, trying to see fine detail on the phosphor screen, extraneous lights are not favourable. So it's quite different to an SEM where you operate in a lit room. In a TM, you make everything dark because you're looking at everything on a phosphor screen. It's quite dim. And then I'm just going to note the dark current and the emission currents of 95.7 and 112.8. Okay, so just a bit of summary what I've just done. There's the logbook. We have to fill in all these different details. Things like the project number, the time that we started, the alloy, the techniques that we're going to, sorry, the specimen. We're doing an alloy. The specimen, the holder that we're going to use, the cleaning recipe, all the pressures, whether all of those things were at spec, the pressures in the different parts of the microscope, and the voltage that we're going to use it at, and the different currents at the start of the session. And then we have to fill it all in again at the end of the session. So anyway, that keeps a log of the operation of the microscope. Okay, now that's done. The next thing I'm going to do, trying not to forget anything as I'm talking to you guys, is I've turned off the pumping station. I'm going to now fill the liquid nitrogen into the cold finger. Okay, so in order to do that, I have to remove the filament that bakes out the cold trap, and now I'm going to pause the video and go and get the liquid nitrogen, put it in there. I bet you can't hear me very well. This is protective gear to put liquid nitrogen into the cold finger. When handling cryogenic fluid, you've got to wear all of this gear as mandated by WorkSafe. Okay, so we grab the little funnel, place it in there, and then we start pouring. Bit temperamental sometimes. As it boils off, the liquid nitrogen spits. So we fill it until we get a little bit of an overflow. That's why we need the plastic sheet. Without the plastic sheet, if we get some liquid nitrogen onto some of the more sensitive parts of the microscope, you can get thermal cracking, and that's not great. Okay, it takes a little while. Okay, I've reached the overflow stage. Just cover that up. Okay, and put it near the vent. So there's a vent over here. Because nitrogen can pose an asphyxiation hazard. So we want to keep the boiling off liquid nitrogen close to a vent. There's big vents in the corners. Okay, now I'm going to stopper this up. Oh, shivers. There we go. And you'll notice it boiling off quite fiercely. And when the actual vessel itself, when the dewar has come up to temperature, or come down to temperature, as I should say more appropriately, there's a final boil off, and it actually is like popping the cork on a champagne bottle. It just goes poof, and it's quite a fun thing to watch. And it does it quite quickly. It's happening now actually, and you'll just see it fly off in the space of about a minute. And once it's done that, it means the dew has come down to the temperature of liquid nitrogen, but there's been a lot of nitrogen boil off, so I'll have to refill it again. So I'm not getting rid of the gear until that's boiled off. It's a bit of a wait. There we go, it's getting more violet now. Yeah, it's getting really quite violent. Here we go. Ah! It didn't blow off. It did blow up, but it didn't actually fall off. 9 times out of 10 it goes poof, and it actually just flies off. But now it's quite calm, you see, because it's reached temperature and there's not as much boiling going on anymore. But because we've boiled off quite a significant amount, I'll have to top it up. So that's it. Right. Oops. And now to bring it back. We're back now. And now I can take the plastic off because I've done all the cryo stuff, and I can explain the layout of the control computers. Okay, I'll go from right to left. So on the right hand side, we won't use it today, is the EDX control computer. So that controls the EDX detector and doing EDX in the TM. This is the main control console for alignments of the microscope, Colton controls, or all of the alignments that also translate into the manual panel alignments. So this is basically the microscope flight center. Okay, so this is where we control the whole functioning of the microscope. Then the thing that we are going to be using today, and I'll switch it on, is the Catan computer. And that's got the digital micrograph software on it, from which we'll be doing all our imaging using the Catan UltraScan 1000 camera that sits just below the plate camera. So those electronics of the camera are controlled through the Catan instrumentation bin that make the detector, and that's a DigiScan controller for doing scanning transmission electron microscopy. And we've got various detector controls, CCD camera controls, annular dark field and bright field detectors, and some of the instrumentation that controls the cameras is actually sitting out in the neighbouring room, which is the common control area for the Titan, which is the flagship microscope of the centre. And people don't actually sit at that microscope, they sit outside the room because human presence will cause disturbances that are readily visible on the Titan. On this microscope, this is the second biggest instrument in MSEM, we can sit at the machine, but usually when doing imaging it involves being extremely quiet, and users will often hold their breath while taking exposures because stillness is mandatory. Just to give you an idea of how this room is designed, those are chilled ceiling panels that give laminar flow of the air down the column, so it's not turbulent flow from an air conditioning system. The room is maintained at a steady 19 degrees, and the black walls are basically acoustic foam that stop the vibrations from sound waves affecting setting up resonances in the microscope. Now the wall of that service hutch is not coated in foam, but that's because if you look at the floor, you can see the seam in the foundation there, and we'll get onto the foundations in a second. That does not look parallel to the walls of the hutch, and that's because the wall of the hutch was designed to not be parallel with the opposite wall, so that you can't set up resonance. Okay, there's a specimen preparation bench right there. We'll use that in a second. Little bit more detail about the room. Big heavy wooden doors, and you notice that so this is about that door is about 3.5 meters high. This total height up to the ceiling is 6 meters, and then you notice there's a gap running around at the threshold of the room, and that's a bit of rubber. Okay, that's rubber insulation, because right here in the lab I'm standing on one foundation, the wall is standing on another foundation, and then if I go outside the room, so I just open the door, that slab there, which is of the building, that's the Titan room over there, and this is the area where everybody sits to control the Titan. That's the Titan control. The actual microscope is in behind that sealed vault. Pumping stations, etc., etc. And there is the control electronics for the camera that we're using inside this room here. Okay, I'll get back to the foundation. So now I'm standing on yet a third foundation. That's a building foundation. So on one foundation, the walls are on another foundation, and so you go into the room. It's like a separate building in a building, because this laboratory is on a totally different foundation. And by doing that, you isolate the room and its contents from mechanical vibration. It's absolutely critical. And of course, those are the vents that I was talking about. There's a vent right there. It's got monitoring on it, and there's one in every corner of the room. There's one over there. There's one over behind the high tension tank. You can't really see it very well. And there's the one I put the liquid nitrogen next to when I was waiting for the boil off. Okay, I thought I'd give a bit more detail about some of the instrumentation and control. So that's the Gatan computer, and that's where we're going to be doing all of our imaging, because we don't use film anymore. That's the left-hand control panel for the microscope alignments and probe positioning and imaging conditions. And notice that we've got several modes that we can operate in. We'll be operating in TEM mode. You can also use specialized EDS alignments, nano beam diffraction alignments, and seabed alignments. I very often use a seabed because I'm a seabed specialist. So those are the specimen controls, and deflectors and stigmatism controls. And on the other side, we've got the main Joel control computer. That's all the software that interfaces with the column. You've got a map of the vacuum system. So that's the entire vacuum system with all every time you see a V, that's a valve, and the P is a pump, and then all of the light blue coloured boxes are pumps that pump the column at different points. So That's again focus control, magnification control, deflection control, imaging mode control, specimen position control as well. And we've got 2 foot pedals on the floor underneath the spectrometer, which allow you to tilt the specimen in X and Y axes. So you've got 2 degrees of orientational freedom. So it's like running the whole thing quickly is like playing an organ. So you've got your feet going at 1,000,000 miles an hour, and you've got your fingers and hands going 1,000,000 miles an hour, and also at the same time you'll probably be playing with apertures to get the right imaging conditions. And now that is where the specimen sits. We'll just unclip that and we'll get it ready for accepting the specimen. So that's a goniometer in which the specimen sits. There's the acceptance aperture, and we'll now get into mounting the specimen.